So the next part of the discussion here is imperfections in solids, or simply we can put it in the form of defects in solids. So when you go for defects in solids, that is crystal defects, we can also call them as crystal defects, particularly properties associated mainly with the metals. So if you go for the classification of these crystal defects, so here if you take classification, that is classification of defects, that is crystal defects, you can put it in this format, that is defects are of, simply if you go with defects or imperfections, if you go for defects or imperfections, you can just take it as, that is, one is stoichiometric defects, and here interstitial, we can take okay, I'm just going like this, non-stoichiometric, I can say non-stoichiometric defects, stoichiometric defects and non-stoichiometric defects. And also we have impurity defects. So particularly let us concentrate here on the stoichiometric defects and the non-stoichiometric defects. Stoichiometric defects, we can also call it as, that is if you go for stoichiometric defects, these stoichiometric defects are also called, that is Daltonoid or thermodynamic defects, because the stoichiometric defects in metals or crystalline solids, they depend on the temperature. When they depend on the temperature, they have certain changes taking place in the crystalline solid with respect to the density, pressure, and its melting point and boiling point, so on and so forth. So based on that, because it is depending on the temperature, because it depends on temperature, it also depends on the heat. When it depends on the heat and temperature, so that means there are certain changes taking place. Based on the changes, we are calling it as thermodynamic, or we can call it as Daltonoid defects. We call it as stoichiometric defects because there is no change in the composition of the crystalline solid. The compositions remain same in the stoichiometric defects of the crystalline solids. So these are of, again, two types. One is Schottky one is Schottky's defect, and the other one is Frankerz defect. Again, if you go for non-stoichiometric, these non-stoichiometric defects can also be called as, just like stoichiometric as how we said the thermodynamic or Daltonoid, here non-stoichiometric we can call it as interstitial defects. These are of, again, two types: metal excess defects, and metal deficient defects. So here interestingly you find here in the metal excess defects we have two types of sub defects again, cationic vacancies and anionic and ionic vacancies. So here also if you go for metal deficient defects, again the same thing is repeated, that is we can go for metal deficient defects, metal deficient vacancies, metal deficient vacancies and metal deficient that is metal vacancies, that is cationic. Here you take it as cationic and here you can take it as metal anionic or simply anionic. Go for anionic and ionic vacancies. So this is a simple classification which we give for defects in the crystalline solids. For impurity defects there is no further sub classification, but the rest of the two defects we find that there is a classification. Stoichiometric defects have two subtypes, that is Schottky's and Frankerz defect, and if you go for non-stoichiometric defects, metal deficient defects and metal excess defects. Defects we have cationic vacancies and anionic vacancies, and metal deficient defects we have anionic vacancies as well as cationic vacancies. So this is a broader classification of the defects taking place in the crystalline solids. So here what we are noticing here is in the stoichiometric defects we have two types of defects. One is Schottky's defect and the other one is Frankerz defect. If you go to Schottky's defect, if you go to the internal structure of the Schottky's defect, what you are noticing is if you take a crystalline solid, the crystalline solid is actually made up of two oppositely charged ions, that is on cationic side A plus is cation and B minus is anion, A plus is cation and B minus is anion. So it's something like an interdimensional, that is three-dimensional network where the cations and anions are strongly holded against each other or binded against each other through the electrostatic force of attraction. And you know very well that the intermolecular force of attraction is very high in the case of, that is electrostatic force of attraction is very high in the case of the ionic solids. I mean to say in both the cases, particularly if you go for Schottky's defect, you are finding that I can say that sodium chloride, potassium chloride, cesium chloride, potassium bromide, all these are more of ionic. These are completely ionic solids. In ionic solids, the electrostatic force of attractions are much more stronger. Relatively, if you take the examples of Schottky's defect, that is in Frankerz defect, the examples are zinc sulfide, silver chloride, silver bromide and silver iodide. So I can say that relatively when you compare the ionic nature of this particular examples, if you take, these are purely ionic solids and these are covalent solids. So there is certain amount of polarity. I can say that there is certain amount of polarity. The cation is able to show the polarizing power and the anion is able to show the polarizing ability. So anions always shows the polarizing ability and the cations tries to polarize the anion such that there is a distortion in the electron cloud, and that results in certain amount of the polar covalent molecule wherein which there is a distortion in the electron cloud, thereby the metal part of the crystalline solid will acquire positive charge and the non-metal part will acquire negative charge. So I mean to say here the percentage of ionic character in the zinc sulfide, silver chloride, silver bromide and silver iodide is quite little bit lesser compared to that of that is sodium chloride, potassium chloride, cesium chloride and potassium bromide. So what difference we are noticing between these two defects? What is happening here is in the case of Schottky's defect, if you carefully observe, you are finding that complete missing of, if you select the position of the cationic positions and the anionic positions, each cation and anion, therefore they are called as lattice points. So if you consider the A plus ion and B minus ion as a lattice point, so I mean to say if you take sodium chloride for example in the stoichiometric defects, among all these examples, if I am selecting NaCl, then NaCl gives one Na plus ion and one Cl minus ion. So what we are noticing here is if you consider Na plus as cation, A plus and Cl minus ion as anion, B minus, you find that there is a complete missing of the cationic site. At the cationic site, cation is missing, and at the anionic site, anion is missing. So this is anionic site, it is anionic site, and here it is, this is cationic site. Of course, it's a vacancy defect. It's vacancy defect because this nothing is there at that particular position. So therefore, we call it as vacancy defect. Here also it is considered as vacancy defect, but here the vacancy defect is anionic site, and here the vacancy defect is cationic site. So you find that there is complete missing of the both cation as well as anion from the crystal lattice, and because equal amount of cations and equal amount of anions are being missed from the crystal lattice, we say that in the short case defect always there is an electrical neutrality being maintained. So because of the electrical neutrality, what is happening? The conductivity tries to increase. The conductivity will try to increase proportionately by undergoing certain ionic mechanism. What is ionic mechanism means? We can consider this as the ionic mechanism. So, and one more thing what we are able to understand here is, this is called crystal radius ratio. The radius of the cation divided by radius of the anion is equal to 1, we said. When we are saying 1, it means that there is not much difference between the size of the cations and size of the anions. Both the size of the cations and size of the anions are having relatively close size. Because of the same size, the crystal radius ratio is equal to 1. When the crystal radius ratio between the cation and anion is equal to 1, then the coordination number is automatically, it's going to become high. So the high coordination numbers, the compounds with high coordination number always favors. For example, cesium chloride has the coordination number 8 and sodium chloride has the coordination number 6. So therefore, what is happening here is usually the short case defect, because of complete missing of cations and anions, you find that the high coordination number is favored, and that is because high coordination number is because of not much difference between the size of the cation and size of the anion. Then we call this as vacancy defect because there is a complete missing of cation as well as anion from their respective sites. Then because overall you are finding that one complete missing of cation and one complete missing of the anion, it affects the entire density of the crystal lattice. When the missing of cations and anions always leads to the lowering of density, so therefore you find that here there is a decrease in the density. When there is decrease in the density, it also shows the impact on the lattice energy. The crystal lattice energy of the crystalline solid also decreases. Lattice energy is nothing but the amount of energy which is required to break the strong electrostatic force of attraction between the two oppositely charged ions. So when the lattice energy is decreasing means little amount of energy is required to break the cationic and anionic force operating between both the ions. Then also it affects the stability. So the stability of the crystalline solid also will decrease. So these are all some of the comparing and contrasting points for the short case defect. Now from there we will go to the Frankerz defect. In the Frankerz defect, we are saying that the crystal radius ratio, that is ratio of the radius of the cation to that of the radius of anion, is less than 1. We are saying this, that means that is large size difference between the cationic and anionic species in the crystalline solid. So it always favors, because of that it always favors the low coordination number. For example, if you take zinc sulfide, the coordination number is 4. And because of that, and just because you are finding that, in this Frankerz defect, you are finding that the missing cation, it is going to create the vacancy defect. The missing cation from the cationic position, cation in the form of lattice point, from the cationic position, it is going to dislocate from that position and it enters into the interstitial space. Interstitial space is nothing but the vacant space available in the crystalline solid. So that the interstitial space is now occupied by the cation, and that cation, because it is occupying the interstitial space, that is why it is giving a defect called interstitial defect. So thereby this empty space is now called as vacancy defect, and that is why, because it is able to shift the cation is not completely missing from the crystalline solid. It is not missing from the crystal lattice. It is just staying inside the crystal lattice, but it is just going and changing its position from the lattice point position to the empty space, that is at the interstitial position. That is why it is just trying to dislocate its position, or it is just trying to change its position from the lattice point position to the empty space, that is interstitial position. That is why this Frankerz defect can also be called as the dislocation point effect. The dislocation point effect means here the cation is just shifting its position from the actual lattice point position to the interstitial space. That is why we are calling it as dislocation point effect. And in the meantime, it is very clearly understood that now it favors all the crystalline solids whose coordination number is low, because there is a large size difference between the cationic and anionic size. We can definitely say that it favors the coordination number. It has low coordination number because the cationic site is not missing from the crystal lattice, it is staying within the crystal lattice. The density of the crystal lattice is not affected. So density of the crystal lattice or density of the crystalline solid more or less remains constant. So because of the density is remaining constant, it shows impact on the dielectric constant. The dielectric constant of all the solids which are showing Frankerz defects will increase because of the closeness of the like charges and the repulsive forces dominate. So therefore you find that there is increase in the dielectric constant for the overall crystalline solid which is showing the Frankerz defect. And those are the examples which we have understood in the case of Frankerz defect. And one exception is silver bromide is a solid where it shows both Frankerz defect as well as that is Schottky's defect. So silver bromide is an exception. AGPR is an exception. It is an exception. This silver bromide, it shows both the Frankerz defect, that is Schottky's defect it shows, and also it shows the Frankerz defect. So in this way we are able to learn thoroughly between the differences between the Schottky's defect as well as the Frankerz defect. So here let us go to the second part of the discussion, that is non-stoichiometric we go to the non-stoichiometric defects. Non-stoichiometric defects are also called non-stoichiometric defects. These are also called as, that is, interstitial. All non-stoichiometric defects are also called interstitial defects. Composition of the crystal, the composition of a crystalline solid is variable, not fixed. Then suppose, for example, if you take some examples like FeO is ferrous oxide. If it is ferrous means it contains +2 is the positive charge, the oxygen state of iron is +2 and the oxygen state of oxygen is -2. So if that is the case, but you find that 1 atom of iron ferrous oxide actual ratio is 1:1. Actual ratio is 1:1. If it is showing the ratio of 1:1, then it is stoichiometric. The compound or the crystalline solid is going to become stoichiometric. But actually, because of its non-stoichiometric nature, this FeO is already non-stoichiometric. So actually its ratio now it is going to become 0.94:1. 0.94:1 means 1.00, 0.94. This is 6. This is 9. So this is 0. 0.06. That means you are finding that a variation of 0.06. A variation of 0.06 amount of the iron, the part of 0.0 variation of 0.06 parts of iron, is observed in the case of ferrous oxide. So there is no guarantee that in ferrous oxide iron is always 0.94:1. Sometimes it can be even 0.93:1. If it is 0.93, then the variation is of 0.07 parts of iron. That means the composition of iron in the ferrous oxide is not fixed. So therefore such compounds which do not have fixed composition, such crystalline solids which don't have fixed composition or fixed parts of the individual atoms or individual elements of a given crystalline solids, if they are not fixed, if the ratio is not fixed, if the composition is not fixed, then such compounds we can call it as there is non-stoichiometric compounds or interstitial compounds. So the defects comes under non-stoichiometric defects and that is interstitial defects. So in this scenario here we have to discuss two parts, that is A, that is in this non-stoichiometric defects. First we'll go with metal excess defect. In the metal excess defect, if you go for the metal excess defect, in this we'll go with the, let us go with anionic vacancy. If you go for anionic vacancy, you take a crystalline solid, you're taking a, suppose let us take, I'll give you one illustration. If you are speaking about the anionic vacancy of a crystalline solid which contains the cations and anions, suppose for example I am taking sodium chloride. Sodium chloride by adding sodium, it is heated. When it is heated, you find that it forms, this sodium chloride, it forms actually something like, you know very well that Na plus of Cl minus, this is a crystalline solid, it is a crystalline solid. So now we are adding sodium. So one of the anion here, what we are noticing here is one of the anion, what is the mechanism taking place here? So from the sodium chloride, the Cl minus will interact with Na plus sodium vapor. If it is heated strongly, it will lose one electron, and it interacts with Cl minus ion and it gives away one electron. How this mechanism is taking place? Actually what is happening here is, if you take sodium chloride, when you are adding this sodium chloride, when you are adding sodium, metallic sodium to the sodium chloride, and when you are heating, you find that now it is going to acquire the yellow color. The entire sodium chloride is going to acquire yellow color. It is because of this is the mechanism taking place. So what is exactly happening? Suppose for example, I am taking a crystalline solid, wherein which it has one cationic site, one anionic site, again one cationic site, anionic, cationic, and again anionic, cationic, anionic, and cationic. Now when I am trying to add sodium and when I am trying to heat it, the sign delta indicates that you are trying to heat. Take the sodium chloride crystal lattice, add sodium, 1 mole of sodium or small amount of sodium vapor you add, then immediately one of the anion will try to move towards the surface from the crystalline solid. It will dislocate and it will move towards the sodium from the internal crystal lattice, from the bulk of the crystal lattice, from the layer of the crystal lattice. The anion will try to move towards the sodium and it will immediately create a vacancy like this. You find a temporary vacancy being created. Cationic site, anionic site, again cationic site, one vacancy is created, again cationic site, again anionic site, cationic site, anionic site, and again cationic site. So what we are noticing here is a vacancy is created. This Cl minus is nothing but, that means now Na plus, this negatively charged site is nothing but chloride ion, the Cl minus ion. If one positively charged pair represents Na plus and one negatively charged pair represents Cl minus, that means the Cl minus ion from this particular place of the lattice point site, the Cl minus ion is dislocating and moving towards the neutral sodium Cl minus, and it immediately forms, the heating is continued. You find that here the mechanism goes like this. So you find that one cationic site followed by anionic, again one cationic. Interestingly, here one free electron comes and settles over here, and this is going to become positive cationic site, anionic site, again cationic site, anionic site, and again cationic site. So what you are noticing here is this is nothing but Na plus of Cl minus plus one electron. This electron has migrated to the the same electron has migrated to the, I mean vacancy the vacancy created, vacancy defect. This is nothing but vacancy defect. So now here this vacancy defect is being compensated. This vacancy defect is being compensated by the defect is being compensated by the free electron. So one more diagram I would like to give you. This diagram shows that positive and this is negative, again positive. So here the migration of the free electron is coming and entering into the vacancy site. So this is electron and this is positive charge, this is negative, again positive, negative and positive. So this electron migration within the crystal lattice, the free electron migration within the crystal lattice, this particular site we call it as F centers. F centers, these F centers are also called, that is Fabian centers, or sometimes they are called as colored centers. Is one of the most important property of the anionic vacancy which is obtained due to, that is the metal excess defect. Like that, each you find that in metal excess defect, you can take NaCl, KCl, lithium chloride. Different solids will acquire different colors. Here sodium chloride acquires yellow color, this is potassium chloride will acquire violet color, then lithium chloride, that is lilac, something like that. Different colors are obtained because of the following mechanism. So here in the metal excess defect, that is B, extra cations in interstitial, extra cations in the interstitial sites of metal excess defects. So I mean to say, what exactly we are trying to understand here is, in metal excess defect, we are dealing with the, in metal excess defect we are dealing with, that is extra cation and electron in interstitial site, in interstitial sites. So what we are noticing here is, suppose for example, what we are trying to do here is exactly, suppose I am taking here, so say for example I am taking here okay, so one cationic site, one anionic site, again one cationic site, again one anionic site, cationic site, anionic site, again you are finding that there is one cationic, anionic and again cationic site. So you are finding that there is a kind of, all these are binded with the certain attractive forces. So obviously the space available, this is nothing but interstitial space. So say for example I am taking here I am taking for example, let me take say I am taking zinc oxide solid. Before heating it's white in color, but upon heating it finds, you will observe that zinc is getting oxidized and it loses half mole of oxygen gas with the loss of 2 electrons. So what you are noticing is, we are finding that extra cation. So here basically this is a crystalline solid, already it's a crystalline solid, it's white in color. Now because of heating, now it has changed to yellow color, it has even changed its color. So now what is happening here is, suppose if I am taking the crystalline, now after heating, now if you go to the new crystal structure, what you are finding is, suppose I am going to put it in this way, that is Zn 2 plus Zn2 plus of O2 minus, suppose for a convenience I am taking, again Zn2 plus of O2 minus, Zn2 plus of O2 minus, again Zn2 plus O2 minus, like this, Zn2 plus of O2 minus, again Zn2 plus. So this is the kind of the crystal structure for zinc oxide. Now what is happening here is, now you are trying to heat the zinc oxide solid, so that means you have an excess of zinc ion, excess of cation, this is excess, this is the excess cation, and these are the excess electrons, these are the excess electrons. So excess cations and excess electrons are again compensated within the crystal lattice. So what I am trying to do is this, when the zinc oxide crystalline solid, when it is heated, whatever the excess amount of the cations and excess amount of free electrons which are produced in the crystalline solid, that excess cations and excess electrons, they are not going out of the crystalline substances from the crystalline solids, but they are trying to dislocate into the interstitial spaces. So I am finding that here I am finding the excess Zn2 plus ion is occupying the interstitial space, that is excess cation. I am trying to place it in this manner, excess cation at interstices and excess electron also at interstices, excess electron also at interstices, this is excess electron also at interstices, this is the point which you have to catch, and this is how the mechanism takes place in the case of extra cations in the interstitial sites of the metal excess defects. This is one of the best example where we can understand. So the next part of the discussion in non-stoichiometric defects is non-stoichiometric defects, non-stoichiometric defects, metal deficiency defects. In this metal deficiency defects we have, that is deficiency of cation, cationic vacancy defect, and here extra anionic vacancy, extra anionic position in, that is interstices. So what is happening here is, like cationic vacancy means, suppose I am just going to put it like this, again same thing, 1 plus 1 minus, 1 plus 1 vacancy, 1 minus, again minus, again plus, minus of plus. So you can see that cationic vacancy is created. Here the difference is, you take a crystalline solid, so here you find that 1 cation, 1 anion, 1 cation, again you can take 1 cation, 1 anion, again 1 cation, 1 anion, cation, and anionic site. So what we are noticing here is, one excess of the anion is introduced, anionic vacancy is introduced. Excess anion is introduced in the lattice. So here what is happening here is, you find that actually if you take some of the examples we can take. Ferrous oxide shows this kind of defect, nickel oxide, nickel monoxide, titanium monoxide, all these compounds, they show this kind of defect. So what is happening here is, like ferrous, if you take ferrous oxide, if you are taking ferrous oxide, it gives out one ferrous ion, and it gives half mole of oxygen gas, and 2 electrons are present. That means once the Fe2 plus ion is produced, it completely misses out, missing ferrous ion, missing ion, this is missing ion, that is cation. So to maintain the electrical neutrality, the ferrous ion in the lower oxygen state, to maintain the electrical neutrality, maintains electrical neutrality. To maintain the electrical neutrality in that is cationic vacancy we find that this ferrous ion is further oxidized. It is further oxidized to ferric ion with the loss of 1 electron. So this ferric ion now that is transported to the vacancy, cationic vacancy, which is created. All the higher oxygen state metal ions, they go and occupy the cationic vacancy, and in this way we can see that the electrical neutrality is maintained in the case of the cationic vacancy defect of the metal deficiency defects of the crystalline solids.